So hello everyone, and today we'll be seeing one of the problem from Gigs for Gigs. It says sum of subarray ranges. The problem goes like, given an array integer ARR, the range of subarray is defined as the difference between largest and smallest element within the subarray. The task is to return the sum of ranges of all possible subarrays. It is guaranteed it's a 32-bit integer. Now we have one example and the explanation over it. It goes like from 1 to 1 I'm having 0, but from 1 to 2 I'm getting the difference as 1. From 1, 2 and 3 I'm getting difference as 2, and so on. With all these possible combinations we get answer as 4. So that is clear that one approach you can do is you can go brute force. You can go brute force in the sense that you can iterate from every subarray from I to j, and thereon you can contribute. You can understand that how this subarray can contribute. Again, this is not an efficient approach, it goes n square. But one thing it gives us an understanding that hey, a subarray can contribute within sum. So it goes with an overall result. So it goes like bit by bit, but ultimately it hits the wall. Do you want that? No. Can we do it better? Yes. How we can do it better? We can understand that hey, whether an element from an array, so let's say a1, a0, a1, a2, a3, and so on. How much a1, or for that matter ai, is contributing, how much ai is contributing to the difference. So the difference can be either two things, either it can contribute in maximum values or in the minimum values, either of them. What is we are interested in? We are interested in the count, and we are interested in the difference. So first of all we can get a count of max and min, count of max and count of min, and once we have that we can get a difference. So minus this. So this will solve our problem very much. How can this solve a problem? This can solve a problem because we understand that hey, ai is maximum within the array range of this 1, 2, 3 and 4, assuming a3 is the last one. And within that let's suppose a2 is minimum, and a2 can contribute in same 4 manners, but it would have its own numbers. So in this way, here simple point is you can see 2 appearing 3 times. That is what 2 is contributing 3 times, which is nothing but 1, 2 and here 3. Okay, yeah. So do not consider this one because this is a result 2, it's not an element 2. So yeah, that's where 2 outshine 1, 2 and 3. The same thing we are doing. 3 is nothing but a count, 2 is nothing but a number. If it is maximum when it is coming with 1, it is minimum when it is coming with 2, 3. So in this way we go ahead and we count, and if you sum it up you get to know that hey, I'm having this number as, I'll take these 3 numbers, 2 minus 2 plus 2 minus 1 plus 3 minus 2. So it will not only go ahead and give you 2 minus 2, but if you take all the pluses and minus differently, so you'll get 2 plus 2 plus 3 one side, and minus on the other side goes like 2 plus 1 plus 2. So this is nothing but the maximums of the window, and this is nothing but the minimums of the window, which we have discussed. And if you ask me an original array is 1, 2 and 3. The rest you are smart enough to understand that hey, this is maximum because within the window of 2 2 is maximum, within the window of 1 2 is maximum, within the window of 2 3 2 3 is the maximum, correct. And when it comes to minimum, within the window 1 1 1 is maximum, 2 3 2 is maximum, and 1 2 3. Yeah, it's similar only. Not sure about that, why it is still like this. It's not this, it's -1. Okay, anyways, so this was a contribution of 2. It was not the entire contribution, so it was a 2's character, but like this we wanted to do for each of the character. So in this way we'll go forward. I'll say return max country of ARR minus min country of ARR. What does this method mean now? This method are nothing but the same thing which we are doing to understand what is the minimum so far, what is the maximum so far. And how can we do that? We can do that with the help of, again, monotonic stack, because we wanted to understand what is the running lower and what is the running higher in terms of number. So I'll quickly go ahead. It will obviously give me an integer taking an array A. For that and for that matter, I'll be using a stack. So I'll go ahead, take stack of integer, stack is equal to new stack. Yeah. Now what I'll do over here is I'll have a number, result 0, and that would be the return result. A size n is equal to a dot length, so that in future operations it would be easier for us. Here the main crux lies that I wanted to go from each element to I is equal to 0, I is less than n, or do I less than or equal to n, I plus plus. You would quickly know that why I'm doing less than or equal to. Just stay with me. Now I wanted to go while I'm not seeing that stack is empty, because I want some element within the stack, and if the some element is existing, then I wanted to know that hey, whether this top element stack.peak, this top element, what sort of element it is. It should be a greater than element. Sorry, it should be lesser than element, because I want a greater element. If it is a lesser than element, then only I can go forward. Either this can happen, again I'm choosing I randomly, I should not do that, and I should check limits of I first of all. If I can be equal to n, or this can happen, either of them. If either of them happen, I am going to update or remove from stack. Why I wanted to remove from stack? Because you see, I currently have a lesser number, I hate a larger number, so I can make space for that. So, and I can have a count till this point. So till this point, how much my top element has contributed, I can take a note of it. So int index was stack.pop, and I wanted to know that how much this index has contributed. So what I'll do is int left is equal to stack.is empty, and if it is empty, it's -1, else stack.peak. When it can be empty, by the way, it can be empty because I hit n is equal to 1. I guess I don't need that, but anyways, I'll keep it. Int right is equal to I. Now I know from left to right how many elements are there. So it's nothing but a count. Int count is equal to right minus left. Yeah. But these are subarrays we are counting. We are not counting just length. This, my friend, here would give you a length which would be just from this point to that point. Do we want length or do we want subarrays? We want count of subarrays, right? So the count of subarrays would be where I'm standing right now. Where I'm standing right now is I. So right minus I, that would be give me current, sorry, yeah, that would give me current position till the right one, and from left I would do similar but I minus left, and ultimately I wanted to multiply them. Okay, sorry, it's not in I, it's index, because I wanted to understand this index, right? Because I'm going for count of this index. Okay, so far so good. So this gives me a count, and I wanted to understand that, hey, for this count how much my result can span. So this count multiplied by a of index, this would populate my result, and this can go ahead and return it. Also, I didn't added the ith index over here on the stack, so I'll just stack push the ith index. That's it. So that was about max contribution. Very same story goes within min contribution as well, where we have a min contribution here, and for the min contribution you don't want it to check when the element is smaller, but check when the element is greater. So rest of the logic stays the same over there, and the only part was this one. Let's compile this one to check any compiler errors we have. Cannot find symbol. Okay, this is interesting. What symbol? It doesn't can find min conti. Oh, it's country ri. This is ri, and this is what it should match here as well. Let's compile this now. It was a minor typo. So yeah, it passed the sample test case. Let me try to submit this with rest all test cases as well. So yeah, it passed all the rest of the test cases as well. This was a classic problem of monotonic stack. As you can see over there, you have stack as a data structure arrays along with space and time complexity. So we have time complexity of n. How do we have this O of n? Even if we have two while loops or two loops, we still have time complexity of O of n, because consider in the point of view of stack, every index only and only once goes within a stack and comes out of the stack. So with that perspective, you have n items, and n items can go into the stack and come out of the stack. The order doesn't matter when it comes and when it goes, but what is important, the number of operation. So anytime for these two loops, even though nested, these nested loops cannot and can never go beyond number of elements in the array, and that's the reason it is O of n time complexity. So yeah, This is one of the classic problem. This, if you are still unaware of it, I would highly recommend you to go ahead and check the area under histogram problem. Maybe you can find the video on your right, and I'll see you in the next one.